Chemical Kinetics lecture part 4. As we know that during the process of chemical reaction, reactants molecules must be collide or undergo effective collision to make a product. So collision theory can postulate the basics of this collision during the reaction procedure. According to this theory, the rate of a reaction is proportional to the number of effective collision per second among the reactants molecules. An effective collision is one that actually gives product molecules. So from this theory, it's very obvious that if reactants molecules collide, but if with not the sufficient energy, it may not be a successful collision to form a product. So if we look into their energetic collision form product, see here, energetic collisions form product, but here something like different orientation. Whatever the original orientation supposed to make product, but it could not. The orientation or direction changes, and also maybe not the energy enough, so they could not get collide and come close correctly to make the product. So the factors that affecting collision theory: concentration and temperature. If we increase the concentration, obviously the number of reactants molecule will be high, which will be ultimately increase the collision with the greater chance of making a product. If we increase the temperature, molecular speed increase, and as a result, high proportion of collision with sufficient force or energy conduct to make a product. If we look into this fraction collision and kinetic energy curve, we can see there is a two curve with the high T2, temperature high and temperature low. If we look into the curve and point out here, this is showing the minimum energy that we need to reaction occur and to make a product. So here the sizes of the shaded, here it's representing the fraction of the collision that involve with the minimum kinetic energy. So we can tell these fractions of collisions of reactants molecule can have chance to make a product. Now, molecular orientation. Why the molecular orientation is important? As we saw the first picture, if we see this ballistic size, we can see that with the sufficient energy collision form product, but this non-energy collisions stay as reactants. I think it should be here. So here we can see the example. Before going to this example, I want to tell something like, let's consider the pen. Let's consider that there is a reaction A plus BC. Here, if A and BC have the sufficient energy, so they're supposed to react and here. So what happened supposed to happen here? So if the reaction process have the sufficient energy and the sufficient collision, so what's supposed to happen here? This bond should be break and this A should be making the new bond with B. So as a result, it should be AB plus C. So to happen this, in fact, we need the correct orientation. For example, that A is supposed to come in contact to B, but if so, should be like that: A, B and C. But if somehow, if it doesn't have the proper orientation and some deformation happen or wrong orientation, so that means the A will not become close to B. So that means this reaction will not happen. Similarly, here we can see the one reaction that actually the reaction was before collision. See, NO2Cl. Yes. So this reaction was before collision. So NO2Cl. I think the reaction is, wait a minute. Yes. So the reaction is actually here. I want to write here. Let's write here. So the actually reaction is this one. So NO2Cl plus Cl. So the product supposed to be nitrogen dioxide plus chlorine. So before collision, then what should be happen? This bond should be break down and these two chloride ions should become close together. So this you can see here, the before the collision, and here also, here during the collision, here they collide. Now after a successful collision, we can see the product form NO2 here and here Cl2. But if we look into here, see, in place of chloride ion, here this chloride ion is come close to oxygen. So that means the correct product will not formed. No reaction has occurred. So this is why the orientation is effective and very important and crucial, and we can see here that how it plays a role to break a bond and make a new bond, that means to proceed the whole reaction. Now we have, if we see here, we already learned couple of things from the beginning of the chemical kinetics, that for successful chemical reaction we need the sufficient amount of reactants to come close together to collide, and also we need the some force or energy to collide. So and also we need the proper orientation. So if the orientation is not proper, that means unsuccessful, you can see here that this is the unsuccessful collision and here is the successful collision. So if this kind of things happen, so we are thinking that our reaction should be proceed, but ultimately it is not working. And here the energy also plays a important role. So if we have energy but not sufficient, so that also the reason and the leading reason that reaction cannot be move on and can be this type of deformation or unstable, I mean not in the correct path. So it should go, if it successful collision, the active energy barrier is crossed, and yeah, so they will overcome those all barrier, and they will be move on, and this is their right path. But if we don't have the if activation energy, see, we can see here, I will talk here, but just see here that if we don't have those activation energy, so maybe they cannot go to their right path, and finally the successful reaction and product may not form. So this is the reaction coordinate with the very poor coordination or unsuccessful collision, and here with sufficient activation energy and reactants come close together, and finally the successful collision and the product form. So here I put the badminton, I mean the tennis racket and ball. When if you have a nice brand new tennis racket, and if you have an old and deformative racket, so when the ball come and you will strike, what happen? Obviously the force for the brand new racket and the broken racket will not same. So this deformation is the similar type of example during the collision of reactants molecule happen when the chemical reaction is under process to run and make a product. So I want to make sure before going to this energy, I mean the energy curve during the progress of chemical reaction, I would like to tell that during the chemical process, we initiate the chemical reaction in the lab, and we can see the reaction procedure by some change or by calculating. Even from the balancing equation, we can calculate the exact concentration or percent of even, and from the data graphical presentation, we can calculate the percent of yield, everything, but still we cannot see what is going on in the intermediate phase. So that's the transition phase. So we know that we start the reaction, we getting the product, and here the transition place, we don't know that we will having the right product or not. We will having right product if we have the sufficient activation energy, that the minimum energy we need to successful collision. That's the main things. And if we don't have, so then maybe they cannot go to the right direction after collision, or even the collision cannot be effective. It can be poor, and they can also be separate, and they can change their orientation. So this transition state, actually we cannot see properly, but this molecular collision theory helps us to learn about these things. So now let's come back here. So we can see here the reactants with some certain amount of energy, and when it comes to reactants to each other with the sufficient energy, then here we go, this level is actually the energy level if to occur the successful collision. So when it happens, then it will come into the right product. So now for completing the total procedure, it involves some energy that we can express in terms of del H, or heat of reaction. So the change of energy in terms of heat. So we know that some chemical reaction we need to induce heat, or we also see some chemical reaction. Let's see the fire combustion or kind of reaction of sodium or potassium in water. We see the violent light, heat. So those are kind of things. So that means that reactions also involve some energy or in terms of heat. So some reaction we may need to induce heat, so and some reaction can release heat. So if we look into this energy diagram and the reaction coordinator progress, what we can see, this is the potential energy. Let's see that kilojoule per mole, and we can see, let's consider that this is the let's take the pen. Let's consider that this is it start from, just consider this is 40 kilojoule per mole. Sorry, kilojoule per mole, just a unit. Let's consider, normally we use. So after successful collision, reactants come close together and we find the product. But if we look into here the product and see the change of energy, so let's consider this is 20. So it seems that we have the equation like del H equal to energy. Let's consider the del P minus del R. We have this equation. So that means the total energy change will be energy of product subtract the energy of reactants, obviously. So we start with the reaction when, let's consider that we had the 40 and when we got the product we find the 20. So in that case we find the del H is negative 20 kilojoule, and this is called the exothermic reaction. So exothermic reaction means it will always releasing the heat from the system to surrounding. So when we start, the temperature was 40 degrees Celsius. So it didn't take the energy from the surroundings. It gives the energy, release the energy. That's why when it's finished, the temperature down in compared to. So exothermic reaction is kind of reaction when release the heat, and always you will find that del H is negative. So I hope that you guys understand about here that we need minimum of energy for the collision. So whatever the total energy change to initiate reaction and to end up to form the product, that we can also call the heat of reaction or change of reaction del H. And some reactions are exothermic reaction like releasing energy. In the next slide we will be see that some reaction, as I said in the beginning, that we need to induce heat. That means we need the external heat. The kind of reaction, they absorb heat from the surroundings. So those type of reaction we will say this is the endothermic. So here let's see the example of exothermic reaction. You know, just remember exo, outside, that always release heat as a fire, light, lots of things. So combustion reaction is the common example of exothermic reaction, like kind of carbon plus when we fire, wood fire or any type of combustion. So this is a example of exothermic reaction. Carbon dioxide plus 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 heat, okay, plus heat, I mean the releasing heat. So within this reaction, not only making the product, but when the product is forming, along with energy is also releasing. So this is the kind of example of exothermic reaction. Now, if we look into here, see another type of reaction. We start, let's consider this is the reactant and this is the energy level, but the product is formed. We can see the product energy is far higher than the reactant's energy. So it seems the product during the reaction process, the product form, but it also at the same times it absorb energy from the surrounding, and this is called the endothermic reaction. And since it takes energy, absorb energy, so del H is always positive. So if we consider del H here, and if we do the same, product minus del P minus del reagent, see, and if we just consider here, it seems that just consider this is 30, if we consider this is like 50, so if we consider that this level is 50, so what will come? So then it will come, sorry, so 50 minus 30, so you will see that del H will be positive 20. So this is how we can calculate the energy, and there are so many reactions happen actually as an endothermic reaction. Like we can see the decomposition reaction. Decomposition reactions, I think you know that most of the time we need to decompose, break down. So we need something external force. Not all, but there are so many decomposition reactions that absorb the heat from the surrounding systems, and these are kind of follow this type of heat energy diagram during reaction process, and del H is positive. I have one example for you, like the calcium carbonate. So if we decompose the calcium carbonate, sorry, I'm having glitch here, bear with me. So we will come the calcium oxide plus carbon dioxide. Kind of example of endothermic reaction. So see, this, as I said, the transition state. I earlier mentioned that we start reaction, we find the product, we can calculate it, the concentration, percent yield, we can even visually see qualitative, and that means we can analyze this qualitative and quantitative, but we don't see the transition or intermediary state. So let's look into here. We will able to see here that what happens. So this is before the start, after completing, and during the process. So this is the same reaction, that chloride and chloride coming together, but when the old bond break and new bond formation, this is a kind of activated, I mean transition state, the some how to say, not permanent, temporary complex form. This is called the activated complex, and this is the transition state of the reaction, and the complex form, it's called the activated complex. So the activation energy that we need to collision and successful reaction to proceed, we can express with the Arrhenius energy equation, and I think you already learned about that. So this is the equation. We can learn the constant, and frequency factor has same units as K. Okay, and here this is the activation energy, RT the temperature, and this is the gas constant. So you may practice some problem, and this type of math problem always come during the test, I have seen. So we can also convert using our logarithm knowledge, and from the slope we can also calculate it, the our activation energy. So here we will see the one graphical presentation of this reaction. The rate constant is mole per liter per second and temperature in degree Celsius, but according to our equation it should be converted into the Kelvin when we will be doing the math. So for just for understanding, I keep the equation here. So if we consider the data table in the last here, they use, I mean the book, we can use this data table and we can find the ln k value and the t value. If we can convert the Celsius to Kelvin like that, and also we need to convert, for this is the linear graph between the constant and the temperature. So we always need to be get ready ln k and inverse t before doing the plot, and the inverse t will always be on the x-axis and ln k will go for the y-axis. And also one thing, that to make simplify the calculation we will add this multiply 10 power 3 so that we can omit the complex part and we may have the easy and straightforward plotting. See here. So please remember, this is the little complexity when we do, and with this type of graph are linear, and as we know that from the slope is the y, you know, the change in constant and the change in the temperature, we can get the value and we can calculate the change of uh, rate constant. So here we can take the line, you know, we can see that it depends on when you will do experiment and you will, that what nice type of line you have. If like that, this is very good. If we don't have, we have to adjust it, especially during the laboratory time. So from this here we can get the value in I mean the temperature and k value, and we can calculate from there the activation energy. We can calculate. Here I want to say that if we want to also calculate the activation energy and the rate constant at a particular temperature that we know, and also at the another temperature that we don't know, so we can utilize this equation and we can calculate also the activation energy. And even if we have the activation energy and the temperature, we can calculate and make the ratio of different types of rate constant. Whatever the problem tells, we can apply this knowledge and we can do that. I hope, though the lecture was little lengthy, but I hope that it will make you very clear about the molecular collision theory and activation energy.